Welcome everyone to the review session for quiz 8 on the harmonic motion. And so there are basically two physical situations in which we have this harmonic motion, that is the springs and RLC circuits. And I'll do one of each, okay? Because it's also, you have to get used a little bit to the wording also of the questions. So first let's start with the spring. So we have a spring. So we have a spring. I'm going to write it a little bit shortcut, but give you all the thing. So an object weighing 64 pounds stretches the string 4 feet from into equilibrium. Okay, there is a dampening. There's a damping of 12 pounds per whatever. And there's an external force and an external force given by the equation 16 t e to the minus 2t. And the object is dropped from 3 feet above equilibrium. So this is all the data, and so now what's the displacement? Okay, so what is y? All right, so first of all, let's quickly review what we are dealing with. So we have the spring equation, differential equation looks like this, right? So where m is the mass, c is the damping constant, and k is the spring constant. F, of course, is the external force. Okay, so what we have here? Well, we need the mass, but we have the weight. So we know that weight is equal to gm. This is on Earth, okay? I could ask the question somewhere on another planet with a different g, right? But okay, we are on Earth here. So 64 equals 32 m. So we see that m is actually 2. The mass is 2. That's very important, right? Not 64, but 2. If you take 64, your numbers are going to be awful. Okay, C, the damping, well, they told us it's 12 pounds, so we know that C is 12. What is K? Okay, so K, we have this extra formula. K over M is equal to G over S. Okay, that comes from Hooke's law. This actually comes from this equation, which says that this is the equilibrium state. When a spring is in equilibrium, means that the force that is acted because of the spring is equal to the gravity. They cancel each other out, okay? And that is exactly what this equation tells me. Let's not go there anymore. So this is then the equality that we have. So in some sense, why don't we, so let's put everything in that we have so far. So we have 2y double prime plus 12y prime plus ky. Sorry, no, that's not what I meant to say. Let me write it, sorry. Let me write it. So sometimes we write this already as y double prime plus, let me not do it this way. Okay, let's just plug it in. We have everything. I don't know why I'm trying to make it more difficult. K we don't know yet. M we know because it's 2. G we know is 32. And what is S? Well, that tells us this is 4 feet. Everything is in feet here, so it's all nice and dandy. So this is 8. So from this we see that K is 16. Okay, so now we can fill everything in. Our equation becomes 2y double prime plus 12y prime plus 16y equals 16t e to the minus 2t. Now, if we can simplify, especially because we don't want a coefficient in front of y double prime, we try to do. We divide everything by 2, so we get actually this. Okay, so this is the differential equation. So already being able to put this up with the right numbers, that already is going to give you some points, right? So our next step is, so if you want, this is step 1, this is the setting up. So step 2, now we have to look at the complementary homogeneous. Okay, we know what to do. That is y double prime plus 8 plus 6y prime plus 8y equals 0. So this is constant coefficient, so we do the characteristic equation. T squared plus 6t plus 8 equals 0. So we have to factor this, and two numbers that multiply to 8 and add up to 6. I think everybody sees that this is 2 and 4, right? So we see that the two roots are t equals -2 and t equals -4. We know what this means. The homogeneous solution is therefore a linear combination of the two fundamental solutions, that is e minus 2t and e minus 4t, a plus b. Okay, these are the two roots, and these therefore are what we do. Okay, step 3. So what are we? 16t e minus 2t. So now okay, so what do we need? The particular solution. How we do this? Well, this is a case where we have basically one of the only cases that we saw is when you have an polynomial times an exponential. And we know that the first thing we want to do is get rid of the exponential, and the way to do that is to look at introduce this parameter u and put the and just put the exponent, but multiply it with that exponential. Okay, but perhaps it's time to point out something. It's not necessary at this point to see it. You will see it later, but it's already good to anticipate what is going to happen. Look, this frequency, so this is, if you want, the frequency of this external force, is actually one of the frequencies of the spring. And so we know that there is some resonance that is going to happen. That's the physical, at the physical side, but on the mathematical side, it means that there's going to be something special going to happen with our differential equation, which we'll see in a sec. But it's good to know that it's going to happen, because that way is a way for you to check that you actually do, that everything correct, the calculation is correct. Okay, we need y prime. Y prime is u prime e to the minus 2t minus 2u e to the minus 2t. Y double prime is u prime double prime e minus 2t minus 2u prime e to the minus 2t, and then take the derivative of the second one, minus 2u prime e to the minus 2t, and plus 4u e to the minus 2t. Okay, we have to plug this all into our equation, so just to put the coefficients here, so we're going to have this 6 times this and 8 times this. Okay, and then just 1 times this, but just... Okay, we know that we can factor out e minus 2t. That's one of the reasons we do this, okay? So what we have then, let's look at this one. So u double prime, you have a minus 2u prime, minus 2u prime. So it becomes like minus 4u prime, okay? And then plus 4u. Now we have to do 6 times this guy. So there's plus 6u prime minus 12u, and then here plus 8u. And that is equal to the other side, that was 8, be careful, it's this one, 8t e to the minus 2t. Good. So what happens, the first most important thing is, of course, that the exponentials cancel. But we see something else happens here. 4u plus 8u minus 12u cancels. So what we have is a differential equation, plus 2u prime, without a u term. Now that is important that we realize that there is no u term, because if there would be u term, then we know that our general solution that we're going to propose would be a polynomial of the same degree, but with undetermined coefficients. But since there is no u term, we have to multiply this with t. So our u, oops, no, that's not what I meant. Our u is going to be a polynomial of degree 1, a plus bt, times t. The t comes from the fact that there is no u term. Otherwise, if we don't do this, you could try, but you'll see you will not get a system. You cannot would be able to determine a and b. Okay, so that is our u, which of course means is at plus bt squared, because we also take derivatives, so it's better to expand this. and so u double prime is then equal to 2b. And now we plug this in into this equation. So that is 2b plus 2a plus 4bt, this guy, equals 8t. Okay, now we compare coefficients. So compare coefficients. Well, the coefficient that comparing coefficients from this with this side, right? The coefficient of the linear coefficient is 4b equals 8, right? These two. But there is no constant term on the left-hand side, so this means that 2b plus 2a is 0. So from this we see that b is 2, and here we see that a, well, we can cancel the 2, so a plus b, a plus 2 is 0, so we find that a is negative 2. So we find that u is equal to negative 2t plus 2t squared. Now be careful, that is u. Don't forget, y is this guy, that's something that people sometimes forget, times e to the minus 2t. Right? This is what we used to do is to box these things so that we can find them back, right? This is where you have to go substitute back in. Okay, so this is our particular solution. Okay, so now step 3 is we have to put everything together, right? So we know that the general solution is the homogeneous solution, the particular solution plus the general homogeneous solution. So that would be minus 2t plus 2t squared e to the minus 2t plus a e to the minus 2t plus b e to the minus 4t. Right? That was the homogeneous one we had here. Good, 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 good. So that is our y. And so now we look at the initial conditions. What did the initial conditions say? Well, the object is dropped from 3 feet above equilibrium. Above equilibrium means that this is at time 0, should perhaps say. That's what is implicit here, right? So at y0, it's 3, right? Because it's dropping from above equilibrium. That's the point, right? So, and our axis is always this way, right? So remember, our spring has been normalized so okay, so this is not the axis, this black line here. So our spring is attached somewhere. Let me not even note the noted attachment, but this is y equals 0. Okay, so it's above. And what is the velocity at prime 0? It is dropped. Means there is no speed whatsoever, so that is just 0. Okay, so we plug in t is 0, then y is 3, and y prime is 0. Okay, so these two plug in, we see, well, the first terms all disappear, so we find that 3 is equal to a plus b, because the exponentials all become 1s, right? So we have to take the derivative now. That's a bit of a nuisance. So y prime, we take derivative of the first one, that is minus 2 plus 4t, e to the minus 2t. Then the derivative, copy the first, take derivative of the second, that is a minus 2 e to the minus 2t. And we get a minus 2a e to the minus 2t, and a minus 4b e to the minus 4t. That's the derivative. And now we plug in t equals 0 and 0. So 0 equals now, let's see, all these terms that I cross out have t's in there, so they don't contribute. So the only thing that I contribute is, and of the exponentials, of course, are all 1. So I get a minus 2 here, that is this guy, and minus 2a and minus 4b. Okay, so our system of equations becomes a plus b is 3, and then if we bring this 2a plus 4b is 3, so a plus 2b is 1. A plus 2b is 1. Okay, so we can do a couple of things. So let's say I'm going to do this times minus 1 and add up by this one. Then the a's cancel, and I get, so this is a b, and that is 1 minus 3, that's negative 2. So I see that b is negative 2, and if b is negative 2, then a is 5 from this equation. Okay, bring the p minus 2 to the other side, and you get 5. So our solution is minus 2t plus 2t squared. This is this part, and a is 5. So I can put this 5 here together because these are all in front of e minus 2t, and then plus b, minus 2 e to the minus 4t. You don't have to do it grouped together, as long as you have all the numbers correct. That's That's great. Okay, so that's our first one. So let's now do an RLC circuit. Okay, so this is a circuit. We can give you the picture. I don't know it by heart. The only thing that I'm good at with electricity is electrocuting myself. No, that's not true, but I did it once as a kid, and that was not pleasant. So that's why I'm never very gung-ho anymore on these things. So we have here a resistor, then induction coil, and then finally a capacitor, and then there might be also a battery. Okay, so this is I'm just going the numbers that we need, RLC, and here we have the battery that will be our F or E sometimes. Okay, and so what is the general equation here? The difference equation here is Q, which is the charge, although what one is interested in is the current, which is a derivative. So remember that I is a derivative, that's the current. That is what one is interested in. So you have to find the current always. Okay, so our equation is LQ prime plus RQ prime plus 1 over CQ equals E. Okay, so that is our differential equation. Now, okay, here's the question. Let me read it for you. Where is it? Okay, so I'm just going to give you the numbers. So we have a RLC circuit, but I put the R between brackets, so without a resistor. Okay, let's say the resistor broke. And so we have what is that called? Sorry. The inductance, L, is 3 Henry. And the capacitance is 1/12 of a farad. Okay, so that's our situation. And there's an external source, the battery is pulsating and producing 24 sine 2t, a current of 24 sine 2t. Okay, so what's going on? I think we're ready for everything. Okay. Oh yeah, no, sorry. And then there's so at time t, the charge is 5 coulomb, but there is no current at time t equals 0. Okay, so let's plug everything in. We get L, that is 3Q double prime, plus R, well, that's 0, so we don't have that. 1 over C, so 1 over 1/12, that is 12Q equals 24 sine 2t. Okay, so we can divide by 3, Q double prime plus 4Q equals 8 sine 2t. Great. That's our equation. So that's if you want step 1, setting everything up. Step 2, now we're going to look at the complementary homogeneous. It's always the same procedure, right? So that is Q double prime plus 4Q equals 0. So the characteristic equation that is t squared plus 4 equals 0. So we see that this t is plus or minus 2i. I hope that's clear. That is a complex number. So we know what the homogeneous solution will look like. This is the omega. This is the frequency. And so we get a cosine 2t plus b sine 2t. Okay, that's how our homogeneous solution will look like. Good, but we cannot determine A and B yet because it's not a homogeneous solution. So we have to now look for a particular solution. Okay, so we know what to do in terms of sines and cosines. If it's sines and cosine, we're looking for a general solution. So y of we take this guy, and we take that's a sine, but whether it's sine or cosine, we're going to have to take linear combination of the sine and the cosine with that angle. But we see again a problem, because sine 2t is already a homogeneous solution. So if I just write this as my proposed particular solution, what's the result going to be if I plug this in? Well, it says it here. It's going to be 0. So what is it that we have to do? So what is happening here is that we have resonance, right? So the frequency of that circuit, because there's no resistor, is gonna, remember, resistor is the effect of damping in case of springs. So this is a non-dampened system that keeps therefore pulsating all the time. But the natural frequency at what it pulsates, 2, is also the frequency at which the battery is adding. So you get, again, this phenomenon of resonance. And so we know that what you have to do is we have to multiply this again with T. Okay? So this is how our solution should look like. Well, and I write Y, and that, of course, utterly ridiculous because we're calculating Q. Okay, so we have to find Q prime. Now, that's a little bit of work because it's always a product. So we have A cosine 2t, the derivative of the first. Now, derivative of the second is minus 2at sine 2t, and plus b sine 2t, plus 2bt cosine 2t, and then q double prime is, by the way, it's good to have this because this is what we want at the end. Don't forget, we need the current, not the charge. And so but still need to take derivative, so that is that's a minus, right? Minus 2a sine 2t. This is I have to do minus 2a sine 2t plus. No, not plus, minus, because the derivative of sine is cosine. So minus 4at. I'm taking the derivative of the sine part now. Right? That's cosine 2t. Okay. Plus derivative of b, well, that is 2b cosine 2t. And then the derivative here, well, derivative of t, that is just 1. So 2b cosine 2t. And then minus 4bt sine 2t. Okay. So we need, what is it, q double prime plus 4 times q. So we need this guy 4 times. This guy we're not going to take into account. It's not there. And this 1 time. So what does this give me? So if you look a little bit, you see there are 4 different terms, like terms. There's a cosine 2t. There's a sine 2t. There's a t times cosine 2t. And there's a t times sine 2t. Okay? And, okay, sorry, and all this then, if we put this all together, has to be equal to 24 sine 2t. No, 8 sine 2t, sorry, I'm pointing to the wrong one, okay? So keep that in mind, okay? So what is the coefficient of cosine 2t? Well, we'll look for the cosine 2t. There's one here. No, there's not one there, Jesus. There's one here. No, there's none in the Q. There's only one cosine 2t, well, there are 2 of them here, that is 4b. And that's it, right? Okay, what about, so this was for cosine. What about sine 2t? We don't look in q prime, because there's no q prime, so we only have to look in q, which has none of these guys. And so here we have this guy, this is minus 4a. Okay, now let's look at what are the coefficients of t cosine 2t. Okay, now we have this one here, 4. Don't forget there's a 4 here, so we have 4a, and then we also have this guy here, minus 4a, right? And then finally, this is 4b, again there's a 4 in front of everything, and this is a minus 4b, and now I have everything, right? And so what we know has to happen, because what is the thing? We know that this is 0, this is 2, and these also have to be 0, right? Because they are not there on the right-hand side. There's only 8 sine 2t. Oh, not 2, 8. The coefficient is 8 here, right? Okay. So, but that's okay, because this is 0, and this is 0. So there's no condition here. I don't run into problems. See, otherwise, if I made a mistake, then I get an extra condition here. There's no a and b will satisfy all this. And from this, it's immediately clear that b is 0 and that a is minus 2. So what is the homogeneous solution is minus 2t, and a was in front of, where are we? No, not the particular solution. I mean the particular solution, sorry. This is this guy here, right? So minus 2t cosine 2t. Okay, so now we look, this is the particular solution. So what is now our general I? Well, as I said, this is the particular solution plus the homogeneous solution. Do we know what the homogeneous derivative is? Well, we know Q. This is the Q, but we don't know yet what Q prime is, right? Q, the homogeneous one. So let's do it quickly. Minus 2a sine 2t plus 2b cosine 2t. Okay? So note, right. So the particular solution we have now found is minus 2t cosine 2t. Sorry. I'm jumping the gun a little bit. Am I? Aren't I? Yes, I am. Sorry. Because I have initial conditions still. I cannot jump. I wanted to jump straight to the current, which we need. Eventually we have to current, but we have to do this we have to take our time. We have to first find the Q general, that is the Q particular plus Q homogeneous. So that is minus 2t cosine 2t plus a cosine 2t plus b sine 2t. I'm a little bit surprised. Wait, let me see. A is cosine. No, I guess it's correct, right? Sorry, let me know. Yeah, it's correct. Okay, so this is our general guy. Sorry, that I had to write it first up this way. Now we're going to use the initial conditions. So step 5, even if you want, the initial conditions. So we know that Q0 at time 0 there was how much Coulomb? 5 Coulomb going through the system. So what is in the system? So what does that mean? Well, if t is 0, we plug this in here. Then 5 equals, well, this term is gone, as is this term, because sine of 0 is 0. And then there's a t there, so we find just a here. So okay, that is good. A is 5. So we also have that there's no current. So I0 is 0, which we know is the derivative at 0 of Q. So we have to take the derivative here. So let's take I, which is Q prime. Now we can take the derivative. Be careful, we have a product rule. So that's that. Derivative sine is cosine, so it is 2. Another 2 comes out. 4t sine 2t. I hope you get where all the 2's and the 4's and the minuses come from. And then minus 2a sine 2t plus 2b cosine 2t. Okay? And so now we plug in t 0, then I is 0. So 0 is equal to minus 2. This term survives. This one is going to be 0 because of the t, and also because of the sine is also. And the other one that we left is plus 2b. Okay, so we see that 2b is equal to 2, and we see that b is 1. So what we find is a is 5, b is 1. But we want the current, so this is what we have here. So let's see what we have now. We have minus 2 cosine 2t plus 4t sine 2t. Yeah, I scratched them out. That was just for this calculation, right? So let me erase these here because they're really there. And what was a? Was 5. So minus 10 sine 2t plus, and b was 1, 2 cosine 2t. And notice, something happens. These cosines actually cancel. Okay, so this is how it looks like. So you can even combine it a little bit. Not again that this is really important, but it's good to see that is what happens. And so you get again harmonic harmonic movement. But if you think about it, what is happening is this is increasing. So the amplitude will increase. So it will be going not very fast, but it will start going up and down more and more. The circuit. So the circuit is at some point going to explode, I guess. I don't know exactly what happens to circuits if they get too much current going through. Okay, so that was the review. So one of the two, and so always pay attention. Okay, on the one hand, it's an application. It's solving these problems in harmonic motion, but it is really a solving problem from chapter 5. Second order differential equations with constant coefficients, and all the methods that we have developed there, taking into account this what happens when you have this resonance. In what the concept boils down to, resonance. And I gave 2 cases here because I like that. That's a little bit special case, so you have to be a little bit more careful, pay a little bit more attention. So most likely you're going to get something like that on the quiz as well. Okay.